All right, welcome to the webinar. Thanks to everybody for being here. My name is Emily Rogers. I'm the Senior Marketing Manager here at KOVALUS. I just have a few notes that I want to go over with everybody about the webinar before we get started. So we have muted everybody just to help reduce some of the noise. And we are using the Q&A feature within Teams for this webinar. So throughout the presentation, if you have any questions, any topics, please put it in the Q&A area as the chat feature has been disabled, and then our team is monitoring the Q&A section. At the end, we'll have a Q&A session where we can dive a little bit deeper into those questions. Also, if you have any technical issues throughout, put that in the Q&A area, and in the background, the team will help you get that solved. So the webinar today is being recorded. We are going to post it to our YouTube channel. Just as a reference, and then by the end of the week, you'll receive an email from the KOVALUS marketing team. We'll have that link in the email. We'll also have a bunch of other resources, and so it's kind of a takeaway from today's webinar. So a little bit about KOVALUS for those who are not as familiar. About 2.5 years ago, we were acquired. We were formerly Koch Separation Solutions. Now KOVALUS Separation Solutions. We went through a complete rebrand, but we have been a pioneer in the separation space for over 60 years. So KOVALUS's portfolio is made up of 3 brands that you can see on the screen. We have KOVALUS Membrane Solutions. That's primarily where we're focused today. So membrane offerings, primarily in water and wastewater, dairy, food, and beverage, but we service over 12 different markets. We also have Relco in our portfolio, focusing on thermal separations. Here it's evaporators, dryers, cheese making technology, focusing in dairy, food, and beverage. And then rounding out our portfolio, we have Ecotech for ion exchange. This is more electronics, metals finishing, lithium, the industrial space. So we are global. That is one main thing about KOVALUS. And I saw on the call today, we have a variety of different people from all over the globe, from Europe, from different areas, US, India. So super happy that everybody could be here. And we have headquarters in Wilmington, Massachusetts. And we also have a headquarter office in Aachen, Germany. We have regional offices, you can see on the screen, in India, New Zealand, South America. And the beauty of that is really kind of how the webinar series was derived. You know, our teams share a lot of knowledge, share a lot of learnings, and we've just really come to understand there's some key topics that are interesting, we hope, to the market, and we wanted to make the webinar series. So that's just a little bit about KOVALUS, and I won't spend a lot of time on that. Mainly, I wanted to help make sure everybody's able to access the guidebook, since that's why we're here. So I'm going to get out of the PowerPoint just for a second. All right, so a lot of people to join the webinar, you probably already filled out this form. This is the operator's guidebook landing page, and this will also be in the email that we'll send out if you have not accessed this. So it's just your basic landing page, and then at the bottom here is where you'll fill out your information. I want to highlight here, I would like a meeting to discuss my needs and how to receive a printed copy. So some people like an electronic version, some people want a hard copy, and that's one area where you can request that. And then our team will reach out and we'll coordinate how to get you that guidebook. So once you fill out all of your information, you'll hit the submit button, and it'll take you to a screen where you'll see this highlighted area, and you'll click that for the technical guidebook, the online version. And it'll take you to this online viewer. So this isn't a PDF, it's an online platform. And I want to highlight here, really important to favorite this or bookmark it so you can reference it and come back to the document over and over. A few features of this viewer that I just want to draw attention to. Down here, brings up its own little kind of table of contents where you can select which page you're wanting to view. You also can type in keywords. So this is a good feature where if you're having something that you want to focus on, it'll tell you how many pages that keyword appears and then give you a sneak peek, and you can click into that and then go right to that page. You can also kind of pin certain pages and things like that. So trying to make it as user-friendly as possible. Also, you're able to zoom in and, move it and be able to see it as best as you need. So that's just a little bit about the guidebook. Just wanted to make sure everybody can access it and see everything that they need. Okay, and lastly, just to reiterate, and this will be in the email, if you did not request a printed copy, but that's something that you want, you can also reach out to this email address if you've already filled out the form. So no need to remember all of this. We'll include all of it. Just wanted to make sure that everybody can access it and a little bit of how to. But why we're here today is the Operator's Guide Troubleshooting Dairy Membrane Systems. And I'm super excited to introduce Dr. Saagar and Dr. Mike. Saagar is the Director of Process Engineering in the US, and Mike is the Director of Process Engineering in Europe and Africa. And together they've really collaborated on this guidebook. They have a wealth of knowledge. And this is something that, in the future we'll potentially add on to and kind of keep it going. So thank you so much for being here, and I'm going to turn it over to Saagar.
Thank you, Emily, for the introduction. Is it clear, Emily? Am I audible? Okay,
yep,
perfect.
Good to go.
You guys can see the screen. First and foremost, I'd like to thank all of you for making time to attend this webinar. So really thank you very much for that. And before we get into the details of what the guidebook has, I think it is very important for us to share here. Forget what's on the slide itself, but the motivation of writing the guidebook. We're all connected here because of the business that the companies have. But at the same time, the primary reason of writing this guidebook is we do have a deep sense of gratitude towards the spiral membrane industry, towards dairy and foods industry. So we wanted to bring together our collective knowledge and try to empower our customers, and that is the most important thing. Empower our customers so they can solve their own problems. At the same time, start creating a dialogue between us and the customers to solve problems, as well as the customers, and they work with other partners to create a dialogue within the ecosystem within which we all thrive. So keeping that in mind, when we started writing this more than a year ago, we did, it was published like about a year ago, but we did make sure the units are all factored in. So you can sit anywhere in the world and open the guidebook and be able to understand based on the units that you're comfortable with. So saying that, so we should get started on what Emily talked about, how to access the guidebook. Here we're going to talk about what's within it. So it goes table of contents, troubleshooting from production CIP, frequently asked questions, membrane exercises, something a little bit about log sheet, loading, unloading of the membrane, and we'll jump into the final part of Q&A session. So table of contents, of course, that goes without saying. This is the guidebook, so you can access the guidebook and see how it's laid out. And more importantly, you may have a frequently asked question, so it's easy for you to access that and see if your question is registered there, and go and try to go to that link in the digital or the hard copy. Glossary on terminology, very valuable for newer employees, operators, engineers, supervisors in your facility. Rather than explaining what a molecular weight is, what a clean water flux is, they can access this. But the more fun that we had while writing this is the synonyms. I can almost talk for a few minutes on this, but essentially we wrote down like how in one part of the world we call it baseline pressure, or a different part you would call retentate pressure, concentrate pressure, outlet pressure, back pressure. I mean, and there are so many more there. There are synonyms for pressure drop. don't even get me started on that. There is differential pressures, DP, pressure drop, almost like if KOVALUS tomorrow, I can't dance or anything, do any reels if when my wife asks me, but I can tell you if KOVALUS opens a YouTube short reel or anything, I can definitely guarantee you 10 to 20, 30-second reels just talking about the synonyms. I just love seeing how differently we all communicate on the same word, how it's communicated 4 different ways. But that's just a little bit of fun. But moving on from glossary and terminology, I think the important part about troubleshooting. So the first part, let's spend 4 or 5 minutes, because while this is a webinar to share with you what's within a guidebook, but at the same time, our interest is to also share something in the webinar today of valuable discussion. So the one of the key things that we are highlighting for troubleshooting on the production is the high baseline pressure, right? And this can happen for those of you who have operated, you would have seen this in many it's very critical. So what is, when you have high baseline pressure, for those of you who are newer, essentially what it means is, the system is designed to run at a certain pressure, and now suddenly you have high baseline, you cannot increase your productivity, or you know to drop your productivity down. And if that happens, you have to first ask yourself, is this a new system or a new membrane? Yes. Then you go and contact your integrator or your membrane manufacturer. If no, then it can be solved. It can happen from 4 different avenues, and it can happen due to 4 different reasons. So we have kind of broken down and said CIP, process, system, and membrane. Within CIP, you can go and look into clean water flux. You review your log sheets to look at your pressures, temperatures, how the pH is, and in different chemical steps. How are you maintaining the chlorine ppm levels during if it's a UFMF especially, and then how your pH stability is holding on the enzyme step. So these are different things that you can watch within it. We can spend time talking about each bullet point here, and we can talk in depth, but just to try to be a little bit more high level view today, those are the things that you need to review within CIP. Now you talk about process. You again look at differential pressures, or like I said, pressure drop, or DP, temperatures, feed and retentate ratios, right? Because you are running, let's say, in some places we call it 2x concentration factor, or 0.5 concentration factor or ratio. So you have to make sure you're running the right ratios of what the system is designed for. And then composition. What I mean by composition is that, let's take an example of like a WPC 80 or an MPC 80 process in dairy. Your analytical can be telling you you're making WPC 80, but in lab might be doing WPC 83, right? So your system runs at a higher viscosity, a higher solids, therefore the baseline pressure is high. So these are also factors where you may be overrunning the protein within the system, causing high baseline pressure, right? Pre-filtration, if your pre-filter is not right, there is some cheese fines, or there is some separator, upstream separator was running with a high fat ratio in this fat percentage in the skim, that can also alter the way the system behaves. It's not able to permeate and flux out much to the membrane, creating the high baseline pressure. And then calcium fouling, which is more centric to the permeate, RONF kind of applications, where you can have calcium fouling as a function of temperature, temperature, pH, and concentration, and so on. And there is a section which is detailed within the guidebook, just talking about calcium fouling with pictures. System, what are the different things that can come from a system? Undersized system, that's possible. You'll contact your integrator. Retentate valve issue, the valve is malfunctioning. Permeate and retentate back pressure. Let's assume the system was built, because we have to think about the high baseline as not only like immediately, right? It can be happen 6 months, 8 months down the line. Maybe you change the silo, or some line changes took place in order to run your plant more efficiently in other aspects and avenues of the plant operation, but that's created a back pressure on your permeate of the membrane system, or the retentate back pressure. Maybe you're pumping it over to a silo which is much further away. That creates a back pressure. it in turn comes, it trickles back into your system, and that creates high baseline, and so on. Programming, for those of you who have worked on systems, you know how critical programming can be. And your programming, there are a few different ways to run programming. We know a lot of companies do a great job, but still there might be some programming errors which may have taken place. So you may have to review that. Membrane, it can be an incorrect membrane. What we mean by that is we have seen very rarely that in a UF machine, there is an RO membrane. So your flux will be low, baseline will be high. But it happens rarely, but can happen. Or your system needs a 10K membrane, but you put a 5K. That can have an impact of 20-30% flux drop, and that can create high baseline pressure. So incorrect membrane. So that's certainly new membrane installation. You'll go back to contacting integrator or membrane manufacturer. If it's a new membrane. Membrane storage, if the membrane were bought 6-8 months ago and they were not installed in the system yet, and they were stored in incorrect conditions, that we as membrane manufacturers or others are giving you a storage guidelines, then that can also create in a reduced productivity, creating high baseline. So these are different avenues, and what we want is for you to review each of these and try to find out where the issue might be coming from. Membrane leak, this essentially happens. So you start and you spot a leak, you check the side glass or permeate tube, and then you identify the vessel. And within that vessel, you try to find, maybe change out your O-rings or lip seal. They may be pinched or cracked. And then you put everything back. Is it still leaking in the next production cycle? Then you can, or you may not, but you have the option to do probing, where you collect a sample out of the permeate line. You put a polytube through the vessel, and you collect samples step by step across each membrane. You can feel it as the polytube is going through the ATDs. It is something we have to mention, that this is only done through the permeate side, where the pressure is like really low, less than 1 or 2 psi or 0.1, 0.2 bar type of stuff. It is a safety hazard to open a cap. So please do consult the right teams before you do this. But that is feasible. It is feasible to identify maybe just one membrane is leaking in the back or something in the end. Other reasons could be membrane damage itself, high pressure drop, high cross flow, chlorine oxidizer damage, permeate back pressure, which can result in permeate tube crack. No soft start on pumps. If you don't have a soft start, you get a hammering on your system, and the last membrane on the vessel can crush. So those are different causes. I think we're good to cover a couple of them. We have covered other things like insufficient pressure drop, not getting the right cross flow. It could be a gap between the membrane and the vessel, and then other reasons, other troubleshooting production things are mentioned are black particulates like lactose burning. If you have a steam heat exchanger within the system, it can burn the lactose, and then that can create plugging on the spacer and prevent proper cross flow. So those are different things. Troubleshooting CIP, that's we did touch a little bit on CIP, but we'll talk separately in detail about. So what is that troubleshooting CIP? So the point that we selected for this webinar, as you guys have realized, the guidebook is 60 pages. We're not able to cover everything of the guidebook, but we're trying to cover about 10 to 15% at best, and selecting key things that we still want to discuss today and have it engage in a dialogue and try to help through the webinar. So CIP flux decline, you identify what the root cause is. It could be a front stage fouling, front loops or stages, or it could be a back stages or other reasons. Front stages typically comes from pre-filter issue or upstream issue. Back stages can come because you over-concentrated the solids or protein, increased viscosity, your analyticals didn't pick it up, or very briefly for a few hours, the operator is new and they concentrated more protein. So it can intermittently create a low flux, high viscosity in the back stages. and that can lead to improper CIP on the back end, because CIP, the chemical, our chemical partners and suppliers, they tune the dosing rate all for a certain recipe. So if you need more CIP or dosage on that day, you may have to look at it. So other potential causes can be stage malfunction, stage pumps, recirculation pumps, boost pumps. Membrane efficiency drop. There can be a glycol leak on interstage cooler, which is difficult to clean, or at least the CIP does not keep into consideration cleaning glycol. So there can be a glycol leak. Stage valve malfunction. Let's say your inlet outlet valve, or in some parts we call it inlet block valve or outlet block valve. Stage isolation valves are malfunctioning. One of them. You don't get the right cross flow. Incoming water quality, which of course everybody understands, which can be hardness in the water, silica in the water, and so on. Troubleshooting membranes. I don't know if we need to sit and deep dive into troubleshooting membranes. What we have done is we've tried to give you pictures. As you can see, these are figure 9 from the book and so on. But membrane crushing, spacer extrusion, the reasonings for it, poor pre-filtration, high pressure drop, so on. But the idea of giving you a lot of pictures is that you're able to use the pictures to train newer operators and to show them, because we don't want you to experience this and then come and train your people. We want to show you pictures on how it looks if something wrong happens. So you can use, get copies, train your newer folks on a rotation basis if you need. Show the pictures on what should not happen and what the reasonings could be. Same thing for channeling. This can happen from a membrane defect, but there are other reasons as well. Again, use the pictures that are available to train your personnel, to train your teams, so they know what they're looking at if something like this happens, and you're not waiting for something like this to happen. Selected frequent asked questions. I mean, like we said, so that covers our troubleshooting section. While we were writing, we did feel that there was a lot of FAQ. It was a good place to write FAQs. Again, with the same point of view of providing you a training tool, a training guide. So we have selectively used some FAQs today. There's probably 20 or 25 or 30, I don't remember, but we've selected about 4 or 5. How to choose mill spacer, or why do we have different mill spacers in a system? As you can see, a spacer, a feed spacer, again, different parts, we call it feed spacer or Vexar spacer. That's not very often used, but 30 mil, 45 mil, 62 mil. The thickness increases, the spacer thickness directly results in having the ability to run more viscous solutions and higher solid solution. So if you think about an example of WPC80 or MPC80, you have much more liquid whey running here, and this is a 45 spacer where you probably running around the 65, 75 dry basis protein, depending on the solids too. But at the end, you have a 62 or 65 spacer where you are running viscous solution and high solids. Fun fact, we also have written down an FAQ about what's the difference between 30 and 31 mil spacer, what's the difference between 44, 45, and 46, and 62 and 65. Because there's not a lot of difference. It's just the terminology that our company uses 30, 45, and 62. Someone else might use 31, 44, and 65. So we try to even address those kind of questions. What are the components within housing? This again is value add for training somebody if they haven't seen it, or when they open a vessel to load membrane newly, that they can start to identify and say, oh, this is what an ATD is. This is an end plug. This is where the permeate, permeate comes from, and so on. So this is just all the components that we typically see. Of course, you may have a 4-long or a 5-long housing, but for example's sake, we've only used 2 long. We also have 3D cutaways along the same lines, just from the feed end, from the permeate end, just to give you added value on training and on seeing what are the different components before you open a housing and try to load membranes as a team. What is pressure drop and how to calculate? Often when we provide you data sheets, we tell you on a 30 mil, you run 15 PSI or 1 bar per element. On this spacer, you run 17 or 18 psi and 1.3 bar per element. So, but your system has to run for all consecutive membranes in series within a housing. So we have written down here an equation to say inlet minus baseline divided by number of elements. For those of you who are probably been in this industry for more than a year or so, probably already aware of this. But for those of you who are newer, they just can calculate what the pressure drop or differential pressure or a DP needs to be. So while we are talking about FAQs, something we consciously wanted to do is we want to engage even some of our customers and readers and our partners, but readers essentially who are interested in more than FAQs. So like we identified and said there are 20% of the questions, let's say, are things that are frequently not talked about, but interesting to read and understand that the things that are happening or that happens in the industry. So why are MF vessels short? MF vessels, for those of you who are running a WPI or like a micellar casein product, I'm talking more on the spiral side, are familiar with MF. But for those of you who are not, it is essentially a process to permeate the protein through the membrane. It isn't to concentrate the protein like we do on UF, WPC UF or MPC UF. It's to permeate the protein. So you have to run it at low pressures in order to have the maximum efficiency of the protein going through the permeate. So you have to run at low pressure. So if I have a 4 long or 5 long housing, we have to run at higher pressures because you have to run 1 bar or 15 psi per element. So automatically you cannot control the average or the TMP, average pressure or TMP. So, but if you run it at low pressure, then you have the ability to control the pressure. And so lower operating pressure is valuable. So this is a 2 long or 2 membranes in series. And this is center fed MF with permeate going on both sides. You have even higher control of monitoring, managing pressure. So that's why MF vessels are short, to control the pressure, to create maximum efficiency of permeating proteins, particularly whey proteins. So, so the next thing is, how does each system start up on UF and MF? While many of you are aware, but we wanted to give a pictorial view of it. So you can see here stages 3, 2, 1, and the green essentially highlights that the stages are open and the red is yet to open. So for UF and MF, typically the system starts from the back end to the front end because you want to build the viscosity and solids on the product, not come the other way from the front, because you cannot afford to build the viscosity at the front and foul the membranes and not have the ability to run for 20 hours. And this is generally, I'm talking about UFMF, not the RO and NF, RO or nano. But in UFMF, you want to build it from the back end. You build the viscosity and you keep going to the front end. But what are the triggers for it to open stages? And we have tried to show you in a graphical format. You have a baseline pressure and you have a time. And every time, so you open up a stage 3, and then once the viscosity and solids built and the permeate flux, which decreases because the water is all gone, and then the permeate flux decreases, the system's pressure keeps climbing because the liquid doesn't have any place to go. Then you open up a stage and then the pressure drops because you are opening up a stage, giving more membrane area for the product. And then the pressure drops. And then again, as the solids and viscosity builds up, you're increasing the pressure. And the pressure increases again because the liquid doesn't have anywhere to go because the membranes are getting fouled. You can say foul depends on what fouling is. There is a certain fouling you will see depending on the viscosity. But once that happens, you have to provide, the system is asking for more membrane area. You open up a stage, the pressure drops, and then it keeps going on. And if the system is sized right and designed right, then after some point, you have the right amount of membrane area. This may take 1 hour, this may take 2 hours, this may even take 8 hours. But overall, you have to keep running a standard feed rate the whole time. So that's the purpose of trying to open from the back, and you have a trigger point for stages to open. Other FAQs, why are RO and nano or NF vessels longer compared to UFMF? You're more welcome to read it. Why are 5 kD and 10 kD so relevant in the dairy space, at least? What is the relevance of high temperature elements? And many other questions are at your disposal for in your literature. Now we go to membrane exercises, and if we didn't if we didn't introduce you, Dr. Droplet. For those of you who joined our webinar at the very start, you would have seen Dr. Droplet is actually kind of supervising this webinar for us. But essentially, he's very serious about the PPE. So safety first, PPE first, and let's go to membrane exercise. Membrane exercise is more about it's almost like a exercise that you can do. Your process engineers, your plant engineers, supervisors can do this. It isn't a just do it right now and find the answer. It's an exercise that you can do over a period of months or year in order to find out when is the right time to replace membranes. So we have taken an example of WPC US, and this topic has been talked about in the industry maybe for 7 or 8 years. So it is a sort of a common knowledge today, but at the same time, there are some plants who are still getting up to speed on it, but we have put down some of the details. So what it's trying to tell you is on a UF, you are retaining proteins, right? So, but then how to know when to replace a membrane? So if you look at it details, then what we're saying is that every membrane, it cannot reject or retain every protein. You will have a couple of percent, like 2%, 3% losses, depending on what kind of grade of product you're making, but you're going to have some losses. So the first month, you're especially on a stage or a loop, is to identify what is that baseline loss. What is the loss that will happen even on a new membrane? So you have to analyze the protein in your permeate, know the flow rate, average flow rate roughly of a meter cube per hour or gallons a minute, and convert it to the pounds of protein that you're losing through the permeate, or the kgs of protein you're losing through the permeate. And then on, you do every month, you're trying to do an analysis on the particular loop. You can do loop by loop by loop. So if you think of a spreadsheet, you're having permeate protein analysis for every single stage, and you have a flow rate, flux or flow rate, permeate flow rate, average or certain time point you can choose, like 18th hour of the day, you take a number every day or something along those lines, and you find out what is the loss that you're getting, incrementally increasing loss every single month, so to speak. And then you go and say, what is my loss, which was base, and then what is the loss I'm incrementally getting every single month. Then you factor in the cost of the membrane themselves, and then you do an ROI calculation. So there is a graph that we have kept here where you have protein in the blue trend and the orange is the membrane cost. But somewhere it's somewhere in this window. We would say somewhere in this window, depending on how nerdy you want to be, you want to go deep dive. We have done integral analysis by taking area under the curve and so on. Or I would say in some ways, it can be a much more simplistic way to do it, where you just get a gauge of the money that you're losing on the permeate side of protein and the membrane cost. And in our experience, it also matters on your purchasing routines of the plant. Because you cannot go and just ask to replace, buy new set of membranes tomorrow. So there is a planning involved. The purchaser or the person who approves the membrane would also be involved. Your technical person is involved. So there is a few different moving pieces, but it gives you a very good window into changing in the next 30 days or the next 60 or next 90 days kind of situation. The other things you can do is, as an exercise, is if you are doing trainings at your facility, you can tag all the instruments for training for your team, and there is a functionality, there is a purpose for each and every instrumentation and component within a system. So you can use this as a guide to understand the purpose and functionality of each component and go and tag it. I'm sure we have covered probably like 90% of the components here. Otherwise, just reach out to the person who has provided you the system, or even other partners, whether membrane or CIP partners, and they will be able to explain some of the need of some components and instruments. It's a list of components, what's available in a skid, and so on. We're coming to the back end, but essentially there are example log sheets that are available within the book for you to review and see if you are matching to the log sheet data collection on a daily basis. You can review that for production and CIP, and loading and unloading SOP. There are 2 pages of instructions on how to load a membrane, how to unload a membrane, adding lubricant on gaskets, and how do you put the end cap in. So definitely review that. We've only put down like 3 steps here, but there are more. There are 30 some steps available to review. Emily went through the how to access the copy. Definitely don't forget favoriting or bookmarking, as she mentioned. And then I went through with you troubleshooting, glossary, FAQs, membrane exercises, and with that, I'd like to turn it back to you, Emily. And would you like to screen share, or am I screen sharing still?
Yep, I think you're good.
Okay, thank you.
All right, so like we said, we can't cover everything today. I know that was a lot of information very fast, but we will have an email in your inbox by the end of the week, which will have a recording of this. We'll also have other documents available. Also on the screen there, you can scan the QR code, and that will take you to the landing page where you can fill out the form to get the online version of the operator's guide. Also, if you want to get a printed copy, there's the email address that you can send your request to, and then we'll facilitate getting you that physical copy. So it seems like we have, 20 minutes left for some questions. So if anybody has any questions about the guidebook, any topics like that, please put it in the Q&A area. And I think, Mike, there's a few questions in there already that we can get to. So thank you.
Correct, Emily. Thank you, Emily. Thank you, Saagar. There are some questions. And the first one, Saagar, is concerning design considerations for calculating the right amount of membrane surface area, especially on NF units.
On the NF units, is there a specific on permeate NFs, or is it the high solids NF? Okay. Okay, no, that's. I think this question is it the question is what is the how to calculate the design area, correct?
Yeah, what are design considerations when calculating the amount of surface area needed on NF units?
Okay, what are the criteria to consider? Okay, I was thinking it's asked about how to size up a system, and I was going to say that's definitely something the integrators would like to do it. It's more like proprietary to them. But what are the variables? I think that if I take the question as what are the variables to consider, it would be, of course, the temperature that you want to consider. And I mean, if it, I don't know if it specifies which industry it is, but definitely temperature. You want to consider pressure, the baseline pressure, or what you're comfortable with. As membrane producers, we do say that you can operate your NF machines. Our data sheet will tell you, yes, you can run it at 600 psi or 40 bar or so. But overall, what we have seen is generally people are operating around 20 to 30 bar range, and about like that's around like 250 to 400 psi range. Definitely factor in pressure, temperature. What solids you want to make is very critical. What solids that you're intending to make. And then if you are making a permeate application, beyond a certain solids, you're going to get calcium fouling. So temperature becomes even more critical once you go beyond like 18 to 20% solids. So then that's another factor to consider. There is also a factor of consideration that you have to take into whether this is an 8-inch, 8-inch, or you want a 4-inch module, a 3.8-inch or 8-inch module. And depending on the viscosity of products, if it's a high solids NF system, then some of the integrators partners that we have seen, they're using the 3.8-inch, but it's not necessary. You can use the 8-inch, but we have seen that there's more affinity towards the 3.8-inch. But if it's a permeate applications, we have seen that even 8-inch works. But yeah, I would say in summary, temperature, pressures, what solids you want to make, membrane diameter to some extent has an importance. Yeah, I would say, yeah, I mean, definitely the composition streams are very critical. There is variability always in composition, feed composition streams. So definitely don't forget that you need to identify an average composition stream, or like the worst case, like the worst case composition stream, or the best case composition stream. So make sure you have to take into consideration as well. So I would say that's the best answer I can give at this point.
Okay.
But when you start looking at details, you will get one or two more. So
Yes, indeed. So some other questions. One is concerning the gap size between membrane and membrane housing, and what is kind of, let's say, an acceptable gap before somebody can say that's not right.
okay, no, that's a good question. I don't have like a number to right now. I mean, Mike, would you like to? I mean, I can answer this, but I won't be able to give a specific. So if you're able to,
my experience would tell me, at least on an 8-inch element, that the maximum gap size, where the gap is the biggest, because if you put the membrane in, it's always an eccentric gap, and the biggest
Yes.
one is at the top, and that maybe 2-3 millimeters is something which I would call acceptable. If it comes above that, then you will create too much bypass around your membrane element, which is not good for your process and for your process efficiency. Then there is a question, in dairy industry, would ceramic membranes be the best for RO polisher plant to clean permeate streams and recover water separately to use again? Okay, not sure if I understand it correctly, but probably is it if ceramic membranes are good for cleaning permeate from RO and RO polisher plants? That's how I understand this question.
so if I have to rephrase what you read, if it's the client may be having or partner, they may be having a ceramic plant, but they do have RO and RO polisher downstream, and they're wondering if those RO and RO polisher systems run differently than a spiral system, you might think, or is it just probably a question about is the RO? I would say, in my view, I don't know if those systems are vastly different than what is if you have a spiral system upstream like a UF and MF compared to having a ceramic, unless there is probably the ceramic is used for some ingredient quality, which probably does result, because the biggest challenge I see in RO especially, or not RO polisher much, but RO at least, you will see is like the calcium values are always moving. It depends on like what kind of product. If you are in a milk system, then the calcium that comes from milk is much higher, so the ROs run slightly differently compared to them coming from a whey system. So I don't know if there is an ingredient that is the ceramic is being running here that is changing the way the RO that they're witnessing is much different than what they would have had experience on a spiral system. Would you have anything to add there, or you think if we get a little bit more details, we'll be happy to get back with more trying to understand the process a little bit more before we answer questions.
Okay. There's a refinement of that question. What would be the benefit to change RO plant to ceramic membranes from spiral system? This is the waste stream coming from UF and MF to recover water. So I would say, I mean, to recover water, no matter it comes from a ceramic UF-MF system or spiral wound UF-MF system, RO is of course always the best to recover water from those streams. I hope that this is answering then the question of what do you think, Saagar?
Do you when you read that, are we talking about the RO polisher RO because that's the other part which everybody is trying to solve the RO reject from the polisher, the thing that the product that goes to the wastewater discharge. Are we trying to address that as a factor? Because that's a stream that goes to wastewater discharge. People are trying to do recycle of that stream, but still there is a BOD COD discharge which wastewater treatments have the burden of accepting. So there is continuous work going on, or at least there are things that could be done better for the industry as a whole. But I guess the best way I can summarize this is, I think it is a very deep dive question here. So we would definitely encourage for the person who's having this question, maybe have a call with us, or certainly reach out to their other partners. But yeah, we will certainly request that, just in the interest of how deep this question could be.
Okay, we still have more time left for other questions. Another question is concerning clean water fluxes. And the question is, how should a sufficient good clean water flux should look like? Is there a fixed value, or what shall you look at when looking at clean water flux values?
No, I love the questions. So when it comes to the clean water flux, I'm going to say it's probably more closer to like how we talked about the membrane exercise for doing the membrane ROI calculator. I'm not going to that deep dive, but I guess the point I'm trying to make is that, I guess the main point I want to make is, when it comes to water flux, once you install the new membrane, I would get the water flux data for that temperature and pressure in the first 1 week or 2 weeks or 3 weeks. Keep that in your back pocket as very critical information, even if it's just the first 2 or 3 or 4 or something. But keep that data as very critical information and use that as a baseline. Because what we have seen is, when Mike and we have tested internally the membrane flux inside a lab, it works far differently than what we have seen in production. Now, it's easy for us to say at this pressure, at this temperature, this is the flux. But in real time, in production systems, depending on the water quality that is there, depending on how the system is engineered, designed, how the water flux programming is inbuilt, because we have seen there are 3 or 4 different ways to calculate water flux depending on the integrator. So it is very challenging to tell why is this number that we developed in our lab is not able to replicate. So there are at least 3 or 4 factors. So the best way I would say is standardize everything from as best as possible in your process. Do not change the programming on how the water flux is measured. Temperature is the one tricky aspect, I would say, because temperature today might be different than the next week's temperature. So it is a very deep down exercise in identifying temperature correction factors and pressure correction factors. Typically, what we have seen is customers have tried to do it, and they have realized that there are a lot of detailing going behind it. But we are more than happy to work and give you a template to do pressure correction and temperature correction. But the most important thing I would say is identify your water fluxes on a new membrane. Changing water quality. Today you might get a city water, tomorrow you might, or a mix of potable water and city water, RO water. Water quality, the system design, the programming, all of these are very key things when it comes to water flux. So standardizing water flux is more easily said than done in reality. So I would say that's the best way. Identify, standardize everything, find out what your baseline foundation flux is, and then monitor your future fluxes, keeping that base information in mind. And we can work with you to give you temperature correction and pressure correction factors. But mainly, probably temperature is more critical.
Okay, so there's another question concerning cleaning, and it's about why it is not advised to use surfactants on cleaning RO membranes. And the attendee is also asking, they have accidentally used that or done that in the past, and there was no negative effect.
Oh, done that in the past and no negative effect. Okay. So we have covered the more generic understanding of surfactant on RO and NF in the guidebook. It is a FAQ. So I'm glad that we have covered some FAQs. But at the same time, the questioner brings up a great point. They have used it and not seen a big effect. I would say that has been my observation as well. But overall, at least I've been in the industry about 10 years, but I was always told that never to use it all comes back to the type of surfactant. And there is like a non-ionic surfactant and ionic surfactants. And I think the reasoning why the chemical suppliers advise you to not use the RO and NF is because you have, because of the charge that is on the membrane surface, and you don't. So for the RO and F, what happens is that you have a charge that creates an attraction on the membrane surface, and it's harder to clean. So it is due to the charge of the opposite charges of the membrane surface and the surfactant. So that's why there is many times a very clear guideline about you saying you need to use non-ionic in this particular membrane, or anionic anionic surfactant can be used in this membrane. So do definitely review our book for that. But that's where the discussion about using a surfactant change from one membrane, UF-MF versus NF-RO, comes into discussion. However, this person is, they have observed what we have observed, that it doesn't seem to affect as much as the common knowledge is. So I think that could probably best addressed by your chemical supplier. Now, it is very much possible that the chemical supplier that you're working with does not have that charge imbalance or charge effect happening on the RO and NF. I mean, the charge on their surfactant is not negatively impacting your RO and NF and creating fouling instead of cleaning the membrane, or getting attached to the membrane surface and unable to clean. So if you use a different chemical, then you cannot assume that it will work the same way the next chemical supplier, because their surfactant recipe might be different than the one they're using. But it is definitely a very nice observation. So would you like to add anything, Mike?
No, not really. You explained it very well, I would say. Oh, there's another question, and that concerns what should be maximum Brix or CED values for a feed to an RO polishing system, especially when this feed comes from a conventional whey nanofiltration system. So sending the NF permeate to an RO polisher, what should be the maximum Brix or COD limit?
Definitely, again, I must accept that the questions are just top notch. They're great questions, and we love it. But at the same time, unfortunately, we have to run a calculator for this. If I won't be able to tell you sitting here to say, I will give you a very traditional example. So let's say you're doing permeate RO. Permeate NF application going to a polisher, right?
Correct.
Is that?
Yeah.
Okay. So let's assume that the customer is doing 18% solids to 20% solids, right? Which is a little bit more generic. They may be making higher. They may be making 24. They may be making 27. But let's assume 18 to 20%, which is more standardized across the world, especially if they're doing animal grade product. So if you consider that, you're going to get your permeate Brix on the NF. I'm going to say maybe around 0.5 to 0.8 in that range. If your membranes are older, you may see a 1% Brix also coming through, but it's going to be somewhere in that range, in the vicinity of 0.5 to 1% Brix or solids coming to the polisher. So I'm hoping that answers that question partially. The COD part is not something, I guess, unless Mike, you remember a number top of your head. I don't remember this number on top of the head, but I know we can easily answer that question, but it's just not right away kind of situation, So, but it is a calculatable value. You can calculate COD and BOD as an equation for it as a function of the lactose, ash, some NPNs, and some residual proteins. You can calculate COD, BOD. There is an equation calculator for that. And you can calculate the COD, BOD that comes off of that stream. So while I would like to, I wish I knew this number right at the top of my head, but it would have to be something that we will have to calculate and come back.
And here's another question. This time it's about replacing elements. And the question is, when replacing elements, do you suggest changing out a whole stage or individual housings or just single elements? Is this the same for UF-NF units?
So let's assume that you have a, let's just say 5-stage system of UF or MF, but let's say 5-stage UF, and we'll come to the NF and RO, but let's just assume for now you have a five-stage UF. So it's easy for someone like Mike and me and to say, you know what, you need to change your membrane all at once. That's the best way you can do this, and everything you can standardize. And but reality is completely different, right? Because you have to have downtime. You also need your purchaser in your facility who's approving the cost to be able to give you authorization to purchase all membranes at once, right? And we're just talking, I'm just saying 5 stages is the example, but this could be 10 stages and they could have 4 different systems, right? So the decision of technically, it's easy to say to replace all, but in reality, for downtime, purchasing options, how to release capital for the company and do that is not practical. The practically, I would say, where you have to find a halfway point somewhere in between. What we would say is like, you would probably change out in a 5-stage machine. I would change out 2 stages at once and then 3 stages at the other time, or 2 + 2 + 1 or something along those lines. But definitely this whole, what we went through, a membrane exercise can be of value. And the membrane exercise, I know probably I oversold it as there is, you have to do this in-depth equation and, it takes a long time. But to some extent, you can use that guide to have a much more easy guide for you to gauge. As long as you're making a similar product consistently, it is highly valuable to go through that exercise and go into deep equations and have a chart, have a graph. I would highly recommend that. But at the same time, you can use that as a judgment to identify like what your protein in your permeate is, and kind of gauge that as saying, okay, I will replace these 2 stages now and then these 2 a little 2 or 3 months later. So I think practically that's what I've seen work. When it comes to the RONF, I would kind of say the same thing. I mean, it's not much different. So it's easy for guys like Mike and me who are more on the technical process side just ask you to change all, but it's not practical is my view. So if you have any thoughts on it, Mike, feel free. If we have disagreements, it's fine. So
no. In the end, it's of course the question of which of the stages you have is, let's say, performing worse in terms of permeate quality, and if there is one, that's of course the first one you should change.
Yeah.
So it's looking on permeate quality, on permeate protein losses to decide which membrane stage needs to be or should be replaced first. And that's what you explained. So I think I have nothing to add to that.
There was a hand, somebody, I think, I don't know is somebody raised their hand? I'm not sure if.
Yeah, that was one attendee, and we discussed that question already from that attendee. But there's another question I see here, and that's again about CIP, and in particular, it's what is a permissional pH drop across a system during the enzyme recirculation to maintain maximum or best enzymatic activity and CIP efficiency. So probably maybe the question is there a pH redosing needed in some cases to maintain good enzymatic activity?
I think that's again very, very good question. I would say, I think the main factor that we wanted to share through the webinar is that a drop in pH during enzyme. Let's say you're running at a pH of 9.8 on your enzyme process, and if it's dropping through a 30, 40, 45-minute CIP of enzyme, you're having it drop from 9.8, 9.7, 9.6. It's dropping. I mean, it doesn't have to drop that fast, but even if it drops from 9.8 to say 9.6, we do our view is that the drop in pH reflects that you have still a lot of fouling. Because remember, the enzyme step is not the first step, right? I mean, enzyme step is probably the second or sometimes even third step. So you should have got a good amount of cleaning already done on your first wash at least. If not the second, kind of depends on what your recipe is, but you should have got a good wash even on the first step. So typically we do not see the enzyme pH keeps fluctuating and keep going down. What we were sharing was the trend of drop. Whether there is an exact range on how much it drops, typically we have just consulted our chemical partners for that. So certainly we would, I think that I don't know if there is a gauge today on a trend on what the slope has to be on drop of pH. So do you, I mean, if you want to add anything, Mike, but otherwise I would say this is definitely a question that we have to take it up with our chemical partners.
Absolutely, because they are the expert on saying what is the really optimal pH for a specific enzyme or a specific enzymatic product, or what is a good operating range in terms of pH for these enzymes still to be pretty active. Or
Yes,
at which pH maybe a redosing of caustic would be applicable or should be done.
right. But in your experience, if you're say at 9.8, I mean, I have typically seen even if it drops by from 9.8 to like 9.7576, I consider that as like that's okay, that's acceptable.
Yeah,
right.
I would say so.
Yeah, but if it drops by more than a decimal or two, then you know that there is something off, because as most of you may be aware, but pH is a logarithmic scale. So every time you go from 9 to 9.1, it's almost like I think it's like a 10x jump in terms of the dosing. So having it drop from every 0.1 factor is more significant than what it appears. But anything, but you'll still, even if you see a little bit drop, it's okay. But just
okay. Do we have still time for one last question, Emily?
Yep, I think there's one more in there, and then
oh yeah.
Yep, I think we'll wrap it up.
Okay, so last question then. Would it be appropriate to use the same CIP solution for cleaning a reverse osmosis polishing system as the one used for a nanofiltration system, using the same CIP tanks? I guess it's again the combination of an NF waste system and the RO polisher for the NF permeate. So using the same cleaning recipe and cleaning maybe even at the same time with the same cleaning chemicals. Would we recommend that?
Yeah, I would say I have not done that, or I've not seen that being done. But to come to think of it, if you have an NF and RO system, a high pressure system essentially, but as most people know, no chlorine and stuff. So the chemicals and the chemical recipes are different for high pressure or low pressure. Considering that, I do think there is value add, especially if you're saying about the best way I can explain but I would be able to explain it is, and we covered this in our water webinar about 3 months ago, which if marketing team can confirm this, but that should also be on our YouTube channel when we add the webinars. And there was a section we discussed about reusing the final caustic as the first caustic for the next day, right? So in this case, I would say there's certainly value in approaching this to say, can I use the final caustic on the NF? Because the CIP is done, there's not really a lot of soil in that. It's a nice, good chemical which gets flushed out. So we have covered about how to recover some of that chemical and reuse it on the NF system in that case. But here, you could take that final caustic and reuse it into the RO polisher system. And the only caveat I would add is that if your NF system is, say, doing like really high solids, then you would somewhere you will have to work with the supplier, the chemical supplier, to do a dosing check. So that's what we had talked about it as well, that you have to do some type of a strength check of chemical. And if the strength chemical check is good enough, I do think there is value to look at it, to use that. So you almost think of it as like a single tank for caustic recovery, for example. And you could do the same thing for acid recovery, but let's call it like caustic recovery, because that's the easiest thing to do, which final caustic recovery and reuse as the first caustic on a polisher NF. So whether I would say it's a definitely a valuable thing to think about. It's something that you have to do a chemical strength check with. So you would need, there's a lot of moving parts there where you should have a silo to store that chemicals. Of course, this is an operational question then. So the person, the attendee who's asking the question, they may have a setup which is much more fluid and much more easy than what we're talking about. But yeah, definitely, I would say reach out to your chemical supplier. Feel free to reach out to us. We can give you what our experiences have been on these kind of setups. And yeah, it's certainly a viable option.
Okay, good. We are almost 8 minutes over time. So first of all, thank you everybody for your attention, for your good questions, and yeah, have a good rest of your day. Bye-bye.
Is there anything Emily wants to add, or?
Nope, I think we're
About-
good. We'll have
Okay.
the email sent out by the end of the week, like I said, and then we'll have more webinars in the future. So we'll post those on LinkedIn. We'll reach out via email, and we really appreciate you being here. So any interesting topic ideas as well, you can always shoot that to the Get Info email, and we'll take it into consideration. So thanks again.
Thank you, guys.
Bye-bye.
Bye.